In this video, we're going to look at vectors. First, let's start with some definitions. To really understand what a vector is, we need to compare it to a scalar, so let's start by defining those two elements. A vector is a quantity that has a magnitude and a direction. A scalar is a quantity that has a magnitude but no direction. To really understand how these work, let's take a couple examples of both. Let's start with a vector. An example of a vector would be the velocity. If we compare that to the scalar example would be speed. Now we often hear these used interchangeably. We don't always hear the definition or see the difference between the two, but there is a difference between velocity and speed. Velocity takes into consideration direction. So for instance, if I were to say I'm traveling at 20 miles per hour at direction of north, that is a vector because I've given a direction with it. Versus if I just say I'm traveling down the road at 50 miles per hour, that has no direction, that would be a speed. If we use negatives, a lot of times we can use negatives to indicate a velocity. So for instance, if I say I'm traveling at negative 20 miles per hour, that would mean I'm moving backwards, whereas positive would mean I would be moving forwards. We look at some other examples. Displacement is an example of a vector, whereas distance is an example of a scalar. One of the best examples to illustrate this, think about a runner running around a track. If that runner runs around a track, right, we'll use this as a starting and stopping point. If they complete one lap, so they're traveling around the track, they have traveled a distance of a quarter mile. Typically, a running track is a quarter mile long. But if we look at their displacement simply looks at where you start compared to where you end. We started and ended in the same spot, meaning that the displacement is zero. We've taken into consideration direction, how we traveled around that initial point. The distance, we would have traveled a quarter mile. So I always like to make the joke that running is the most pointless activity ever because you always travel a displacement of zero. That's why I don't run. One of many reasons I don't run. So hopefully those give you a couple examples of velocity versus, vectors versus scalars. Scalars, we've heard of scaling factors, I think, a lot. So for instance, you may have seen model cars. You might see a ratio something like 1 to 50, and that would represent that 1 inch on the car would represent 50 inches on, 1 inch on the model would represent 50 inches on the race car or whatever thing we're modeling. So you might see something like that on a model. You would also see that little scale on the bottom of a map that would be showing you, hey, this 1 inch represents 2 miles, this second inch represents 4 miles. And so we've seen scalars before, we've seen vectors before too, we just haven't always called them that. In this class, we've seen things like John walks north for 5 miles and then turns east. What we're doing there is we're giving a vector, we're giving a distance along with a direction. Let's study these vectors a little bit more. So if we want to write a vector, if we want to write an equation that gives us a vector, we're going to have to use a little different notation. Vectors we always write with a little arrow on top of them. So right here you can see that I'm using V to represent my vector, but to indicate that it is a vector, I have that arrow on top of it. And we can break a vector down into two components. We can break it down into its horizontal component, and we use the letter I to represent that, but to indicate that it is a vector, we want to put an arrow on top of that. And then we use a J, again with the arrow on top of that, or what we call the I hat and J hat, to represent those are the components of the vector. So this A here, this is representing the horizontal component of our vector. This would be telling me how much it's traveling left and right. Versus the J component, this is representing the vertical. So let's take as an example, let's write down a vector. Copy this real quick. And this time I'm going to put some values in for those A's and B's. So for instance, let's say that the A is a 4, and then the B, we'll make that a -2. And I want to graph this vector. So if I'm going to graph this vector, I need to start with my xy plane. And so the x-axis here is really representing that horizontal distance. The x always gives us the horizontal. The y is our vertical component. That's going to be the -2 in this case. So what this is telling me, I need to travel 4 units to the right. And I need to travel down by 2 units because I have that negative there. And that would be the point where my vector is taking me to. Now, the important thing with vectors had a quantity and a direction. So we need to indicate that direction. We're going to do that by drawing an arrow, and I'm starting from the origin because that's where I counted from. And then the arrow I'm going to put on that last point that I drew, where the 4, -2 took me to. Now that arrow is not indicating continuation. It's very different than how we've drawn lines or rays before. That arrow is simply telling me the direction because I don't know whether my force or my distance or speed or whatever I'm looking at here, I don't know if it's traveling to the right or if it's traveling to the left. That arrow is telling me, hey, the distance that I'm traveling or the displacement, whatever I'm looking at, that is traveling from the left to the right. Now, why did I choose to start it at the origin? I chose to start the tail of my vector at the origin. I didn't have to. I could have started wherever I want to because vectors don't tell me, they don't give me a starting or ending position. So if I'd wanted to start at this point right here, the point 2, 2, I could have done that. And then from there I travel 1, 2, 3, 4 units to the right, and then I would have traveled down by 2 units, meaning my final point would be right here. If I draw that vector, there it is. Now what I see is these two vectors are parallel. They have the exact same slope. Their arrows are on the same end. But these two vectors would be the same. Vectors do not have a guaranteed starting position. That depends on the setup of the problem. So if we're starting from grandma's house versus if I'm starting from my house, those would give me two different starting points. Now how I travel from there, the vector is going to tell me that. It does not give me that starting position. So what we can say is two vectors are equal or the same if they have the same magnitude and the same direction. So that brings us to the point of, well, how do I find the magnitude or the direction of a vector? So let me come back to my picture for that. If I want to find the magnitude is the amount of this line right here. How far did we actually travel? I'm going to ignore this one for a minute. Let me just get rid of that. We're only going to concentrate with that lower one because that is the easier way to graph it, right? Why would I start at some random point when I could have just started at the origin? So we'll concentrate on that one because it is the easier one to look at. If I want to find this length right here, well, I'm going to draw out my triangle. So I have this side known, that side was 4 units in length. This side here, well, that's 2 units in length. And I've drawn out a triangle. So as we've done many times up to this point, if I want to find this hypotenuse, I can use the Pythagorean theorem to figure out what that length will be. The magnitude of a vector, which we can indicate by putting that v in a pair of double absolute value bars. Those double bars right there always indicate a magnitude. And I'm going to put my v back in there. Well, that is going to be equal to the square root of the a squared plus the b squared. Notice this looks very similar to what complex numbers format looks like. The only difference is we don't have a complex number, right? Even though some of the pieces are the same. We called things a and b before, and we had an I before. Now we're talking about I hats, j hats. These are completely real numbers. Yes, we're using some of the same looking formulas because we're still dealing with right triangles. But we have completely real numbers now. Vectors are completely different than complex numbers. So we want to make sure the second we see that little arrow above the v, and the second we see those hats on the I and j, we have a vector. Versus if we see just the I with no hat and we don't see a little arrow on the vector, that would indicate to us that we only have, or that we do have a complex number. So if I want to find the magnitude of the vector that we just drew on the board, right, or drew on the screen, we can find that magnitude by taking the 4 and squaring that, by taking the -2 and squaring that, And so that will give us 16, and 4 more would be the square root of 20, which we can simplify to 2 square roots of 5. That should be inside the square root. Square root of 20, which simplifies to 2 square roots of 5. Now, if we want to find out the direction of the vector, well, we could find the slope, but that's not real precise because we could have traveled left or right up this vector. And we know it's going to the right, so really a more accurate descriptor rather than just slope, which doesn't tell us the direction along the slope, would be to find the angle. So I'm looking for this angle right here, but of course, because we have a right triangle, we can look at this angle and then we can adjust it according to our reference angles. So if I think about the sides I'm given, I have the opposite, I have the adjacent side. What's going to allow me to find the angle there? We're going to use the inverse tangent. And we're going to take the inverse tangent, while our opposite side will always be the vertical component, so that will be the b, over the adjacent, which will be the a. So we're going to be looking at the inverse tangent of b over a. Now, again, we see some comparisons between these and complex numbers. Just like complex numbers, it's very important that we start with a graph. If we don't start with a graph when we're trying to find this information, inverse tangent does not tell us which quadrant our angle should be in. We can see that it's supposed to be in the fourth, but remember the inverse tangent will give us one of 2 possible positions for any ratio of sides. So we always want to place the angle ourselves, think about where it's going to be. Let's figure out what this one will be. So we're going to take the inverse tangent of our opposite was 2, our adjacent was 4, and it should have been a negative 2 over 4. So we're looking at the inverse tangent of negative 1/2 if we simplify that. So I'm going to pull up my calculator. I'm going to go ahead and make sure my calculator is in degree mode. And now I'm going to take the inverse tangent of a negative 1 over 2. And when I do that, I get the answer of negative 26.56 degrees, which if we wanted the positive, right, it doesn't matter. We can use the negative there, the smaller of the green arrows, or the positive. If I wanted the positive, I could just add 360 to that, finding the coterminal position. And so now I know that the angle should be 333.43, and that is a degree measure, so degrees.